Hello, students. Welcome to Fatigue Analysis. I'm Dr. Stewart. Today, we're going to start a new video series on variable amplitude loading. We're going to touch a couple of topics, including what is variable amplitude loading, what are damage accumulation and quantification methods. We'll talk about cycle counting algorithms, how to make life estimations with the stress life, strain life, and LEFEM approach, load sequence effects in crack growth, and then finally the do's and don'ts. And in today's video, we're going to do the first two topics, variable amplitudes and damage accumulation. Variable amplitude loads, VAL. Service loads are usually of a variable amplitude. This can include things such as aircrafts, automobiles, machinery, ships, bridges, etc., where the loads that are applied to those structures change with time, and they are not always repeatable. This variability comes from the working loads themselves, changes in vibrational loads, as well as accidental loading. It's important whenever we're designing to resist fatigue that we apply realistic representations of service loads in our experiments as well as in our equations. So it's important to accurately measure the applied loads on a component as well as predict the loads in those components that have not been created yet. To measure the load history in a physical structure, most commonly, strain gauges are attached to critical areas on a component. And then that component is subject to service loads or even simulated service loads in a load frame. The data from those strain gauges is read in using a data acquisition system, and the data may be filtered to isolate the primary loads from noise, from vibration, or from line noise. The data is often summarized or compressed by using cycle counting methods, where we take that variable amplitude data and we simplify it so that it's easier for us to use in computation, but also for us to store. Some examples of variable amplitude loads are given here on the screen. At the top, we have an offshore structure. So you could think of a oil rig out in the ocean, and let's say that we have some strain transducers on the legs of this oil rig. We'll see that as the weather changes, going from moderate to storm, mild, high winds, and mild, that the loads that are applied in the legs of that offshore structure vary. They are dynamic with the environment. So that is an example of variable amplitude loading. Another example we have here is for an aircraft. Aircrafts are subject to flight dynamics. There is takeoff, there is climb to cruising altitude, there's cruising speed, there's fall to landing altitude, there's landing, there's also taxiing. But furthermore, the environment, for instance, if there is an air pocket that causes turbulence or a thunderstorm that causes the aircraft to be subject to some high peak loads, that is going to create a variable amplitude load. Another example we have here is for an automobile. An automobile is a system of components, and depending on the part that we're looking at and the sensors that we've placed, we can end up with completely different styles of variable amplitude loading, whether it's suspension loads, transmission loads, or bracket loads in an automobile. Furthermore, we can take the data that we've generated from our components and apply cycle counting methods, where rather than using this raw data that could be sampled at 100 samples a second, we simplify it and distill it into ideas, in this case, ideas of what are some of the strain ranges and mean stresses that are encountered? What are the core peaks and key features observed in this data? Real load histories can be applied to small test specimens and components and subassemblies, or even all the way up to full products by using a closed loop, a servo hydraulic test machine, and designing very specialized fixtures and such. However, those complex real life loads, sometimes they are too complex. Sometimes they are at too high a frequency for us to apply on a sample. In those cases, we can take those complex load histories and we introduce simplified loading, such as block programs and different structures that take very randomized data and create almost like clean averaging blocks across ranges of the time history. And this makes it just a little bit easier for us to control, and as well as a little bit easier for us to calibrate predictive models to. And this here is an example. This is an example from our book of an SAE, Society of Automotive Engineering, a type of load frame for applying fatigue loading into the components of a vehicle. We can see that each wheel is independently connected to a system here. We've got an entire suspension control with servo hydraulics that allow us to simulate road conditions. You can simulate potholes. You can simulate rough surfaces and how that affects the vehicle structure. This here is a more modern example. This is an example of the Boeing 787 wing test load frame. This is where they took a full size Boeing 787 and were able to perform static as well as fatigue tests to look at the aeroelasticity and the redundant design of the wing structure. Another example here is the Lockheed Martin fatigue load frame. Here they've set up a servo hydraulic system that allows you to load up an F-15 fighter and see how different simulated flight dynamics affect the performance of the wing structure and the resilience of that structure. So now that we've kind of got an idea of what variable amplitude loading is, let's take a moment to think about what type of damages accumulate in structures and how we might be able to track damage even when we're subjected to variable amplitude loading. Damage quantification focuses on measuring the damage that accumulates within a material. And damage quantities can reflect and measure the real damage state that a material undergoes. That is a very key aspect that allows us to create cumulative fatigue damage models. Luckily for us, many different damage quantities have been proposed in the literature and by different companies and scientists. Some of the damage quantities that have been used and are continuing to be used are simple things like time ratios, crack quantities such as crack population, crack length, or weighted crack lengths, mechanical properties such as strain, stress, plastic strain, strain energy, elastic moduli, endurance limit, and hardness. And then we move on to the more difficult to measure quantities such as metallurgical parameters, and then some physical measures using x-rays and different advanced techniques. These quantities, these measures that we can take from our material are typically converted into a cumulative damage equation, where that equation evolves from 0 to 1, where 0 means the material is relatively undamaged or it's a virgin material from the factory, and 1 means that a component has reached critical damage. An example here, we have an example of a cycle ratio equation, where we're tracking the cycles as they accumulate and say we know the cycles to failure from a previous experiment. At 0 cycles, we have an undamaged specimen. Once a little n is equal to nf, we have critical damage. We have a value of 1. This same concept is applied to our other damage quantities in various ways. Some of them are ratios, some of them are integrals, some of them may be even some more complex form of equation, but they're all kind of formulated to get us from an undamaged to a critical damage state. And this is useful because what we can then do is we can correlate these damage quantities to our fatigue performance. Here is an example of various damage quantities and how they evolve for a specific material. So one alloy was tested, and all of these measurements were taken throughout the fatigue cycling period. And we can see, depending on the damage quantity we used and its resulting equation, we get different paths, very different paths of what we think or how damage is accumulating from 0 to 1. Some of them are exponential increasing equations, or not equations, but behaviors, because these are damage quantities we're measuring. Others are almost hardening equation, where they harden to the value of 1. So it kind of demonstrates here that if we can identify a good damage quantity, then when we take our samples, say from the F-16 fighter experiment, we can be measuring these damage quantities. We can be measuring hardness, or we can be measuring using some of the different quantities, the physical damage, and compare that to what we end up with as cycles to failure. Now we're going to move into cumulative damage. And this is where we go from taking these damage quantities and measuring from the material to actually trying to design based on some equations. Cumulative fatigue damage analysis plays an important role in fatigue life prediction of components and structures. An understanding of cumulative damage mechanisms is essential since it provides the necessary physical basis for modeling the cumulative damage process. A couple of some of the nomenclature that we need to know. D or DI, that's the damage occurring in a material due to loading. So D is damage. N over capital NF, that is a cycle ratio, where N is the current cycle and NF is the cycles to failure. And then finally, capital D, DN, or the derivative of damage with respect to cycles, that is a cyclic damage accumulation rate. And this is an important parameter and can be even an equation that we use to see how damage grows. Let's start with an example of a variable amplitude load. Here we consider a two-step loading sequence where we have a block of loads at a certain stress amplitude, sigma A1, and then we have another block of fatigue cycles at a stress amplitude A2. Failure occurs when the total accumulated damage in this body exceeds unity. And what we'll want to do is we'll want to measure how much damage accumulates in each of these blocks and add them together to tell us if we've reached critical damage. Now, the rate of damage accumulation can be approximated using a couple of different methods. There's the linear approach, where we linearly add damage from each subsequent block. There's the double linear approach, where we have some dependency on the previous cycling. And then there's the nonlinear damage rules and approaches, where we have completely nonlinear relationships. The linear damage approach, called the Palmgren minor rule, is the classic approach. This is something we see in all areas, not just in fatigue, but in other areas where damage is tracked. The equation states that damage is equal to R times the sum of the damages at I, where I is the constant amplitude portion we're looking at. So I is this first block and, 1 block and 2 block, right? So I is that index. We can replace this damage for each interval by a life rate or a cycle ratio, Ni over capital Ni, comma F, where Ni is the number of cycles in the block, and Nf is the expected cycles to failure if we were to continue to cycle at this fixed amplitude all the way to rupture, right? And Palmgren-Minor's rule states that when damage is equal to this equation, if it's greater than or equal to 1, then we've reached rupture. Then we have failure. Nonlinear damage theories consider load sequence effects. They consider how the effect of the first block of cycling affects the next block. In nonlinear damage theories, we say that the damage in the current block, di, is equal to, in brackets, the number of cycles in the current block over the cycles to failure for that stress amplitude to the power alpha I, where alpha I is a function of stress level and the prior damage, and also can be described as a shaping constant. Now, we can apply this, or how do we visualize this nonlinear approach? Well, let's consider first 2 separate fatigue tests, each run at their own stress amplitude, right? So we have an N1F and an N2F. These are just different cycles to failure. 2 separate, completely separate experiments. As damage accumulates, they each will go from 0 to 1. Now let's consider our 2-step example, where we have 1 cycle set, and then we need a shift to a second cycle set. If we normalize the cycles to failure, so if we go from just cycles to a cycle fraction, we're actually able to see how the first path, the first stress block, relates to the second stress block. And then using this equation, we can figure out how, when we go from the first stress block and we shift over to the second stress block, the accumulation of damage changes. Linear damage and nonlinear damage rules at 3 stress levels are plotted in this example, and it just kind of demonstrates the difference between linear damage and nonlinear damage. In our linear damage rules, it doesn't matter what prior loading has happened, we are linearly summing damage from different blocks together, right? So here we have 3 different blocks, and all 3 of them are just going to add up from 0 to 1. While when we have nonlinear damage, and we're going from one stress range to another stress range, the way that damage accumulates between those different stress levels is different. It is not a linear path. It now is nonlinear, and it's dependent on prior loading. We also have the double linear damage rule. This one is a little easier for us to use. It was developed by Manson and Hafford, and it approximates the curve that corresponds to damage accumulation as 2 lines. And this method here is where we simply introduce a knee damage that kind of takes us from this linear damage to a step change in damage due to prior loading. Beyond the double linear damage rules, there are many different non-linear rules that people have developed. Here is a set of power law-based type of rules. And here, in a paper by Fatimi and Yang, this is a seminal paper written in 1998, they summarize the literature at that state for the different damage rules that have been observed, some of the different rules that have been observed in literature. And see, our Palmgren-Minor rule is one of the oldest. All right. So to summarize, Linear damage is a straightforward and the most often used approach. Palm grain minor, it appears in all kinds of damage problems. But linear damage rules are typically non-conservative because they don't account for the sequence effect of one block or previous damage affecting the next state of damage. Non-linear damage rules require material shaping constants, which must be determined from some stepped stress testing. And typically, because it's nonlinear, it requires a larger number of calculations than compared to linear damage. But nonlinear damage rules give us much better predictions. And so most of the recent work is using nonlinear damage evolution type of equations. Some things to note is that mean stress effect can be considered using a Goodman style approach where we apply the modified Goodman equation and then can produce a fully reversed stress amplitude to use in our original equations, in our stress life equations. And another thing to note is for Minor's rule that the constant 1, so that value where damage must be equal to 1, and that is the critical damage where rupture happens, it is often replaced with a more conservative value, with a value of 0.2 or 0.3, because the linear damage rules are so non-conservative. And this number, the value you use, it can be kind of sensitive to the material. So you want to see for your specific material, what do they consider critical damage? All right. So we're done with our first video. In the next video, we'll get into how do we do cycle counting methods. How do we take that raw variable amplitude data and distill it into something that is useful, that we can make design decisions from. All right, I'll see everyone in the next video. Make sure to hit that subscribe button and turn on the bell to get the latest videos, and I'll see you next time.